Hello, everyone. Welcome back to this live session series on data science with Python. So, this is the last live session in the series, and we've learned everything when it comes to your Python libraries and statistical analysis and also implementing data science algorithms. So, in this session, we'll be doing an end to end project where we'll be doing some data manipulation, data visualization, and then we'll also go ahead and implement some data science algorithms. Let me just go ahead if the live session is working properly. Okay, so I can see the video. Let me also see if the sound is proper. Okay, seems like even the sound is proper. So now that we've done the sound check and the video check, we can go ahead and start up the session. So as I've stated, this will be the final session where we shall be doing an end-to-end project. And we'll start off by loading the dataset. Now, before that, we would have to load all of the required libraries. So I'll just import all of the required libraries. So I would need pandas. So I shall type import pandas as PD. This is what we shall be using for most of our data manipulation work. Going ahead, we'll need some data visualization libraries. So I shall need matplotlib and cbond. I'll type import matplotlib. Actually, we would need pyplot from matplotlib. Let me change that. So we shall have from matplotlib import pyplot as plt, and then we shall also import cbon. So I have import cbon as SNS. So for now, these are the three libraries that we shall be needing. And since we are working with the iris dataset, this is a part of the cbon library. I can just go ahead and load it through that. So there is a method which is called as load dataset. So let's just wait. And then inside this, I'll give in the name of the dataset, which would be iris. And I shall store it in a new variable called as iris again. And I'll have a glance at the first 5 records of this data frame. So if you attend the previous classes, you know what the head method is and what it does. So head method basically helps us to look at the first 5 records of the data frame. And also, if you attended previous sessions, you would know what this iris dataset is. So this dataset comprises of 150 records of the iris flower. And this iris flower has 3 different species. It is setosa, versicolor, and virginica. And apart from the species column, we are also trying to analyze different properties or different features of the flower, which would be its sepal length, sepal width, petal length, and petal width. Okay, so we have looked at the data set. Now I'd want to understand this data set properly. So I'll go ahead and type iris dot describe. So this is a method which shall give me some numerical interpretation from this data set. And as you shall see, this is only for the numerical columns, not for the categorical column over here. So that has been excluded. So here, if you look at the sepal length column, we can see the minimum sepal length to be 4.3 and the maximum sepal length to be 7.9. So the range would be between 4.3 and 7.9. Similarly, we have the sepal width column, and the sepal width seems to be the minimum value is 2 and the max value is 4.4. So the range is 2 to 4.4. And then we have petal length. So the petal length ranges from 1 to 6.9. And then we have petal width, where the minimum value is 0.1 and the maximum value is 2.5. So this is what we understand from this data set. Let's also have a glance at the number of rows and columns. So I can just use the len method, which stands for length, and inside this I will pass in the name of the data frame, which is iris. And this tells me that there are 150 records in this data frame. Now, similarly, if I just give in iris dot columns, this tells me that there are 5 columns. So this is a 150 into 5 data set. So 150 records and then 5 columns. Okay, now I'd want some more information from this. So what I can do is, if maybe I'd want only those records where the sepal length is greater than 5. How can we do that? Well, I will first give in the name of the data frame, which is iris, and inside this, I will give in the column name. So I would actually need sepal length. So I'll change this to sepal length, and this has to be greater than 5. Let's see what do we get. So we get a bunch of true and false values. So here, if you look at this we got to be true because this value is greater than 5. All of these we got to be false because these are less than 5. And that is what we have over here. Now, if I want only those records where the sepal length is greater than 5, so here I just have a bunch of true and false values. What I can do is I can pass these a bunch of true and false values inside the iris data frame again. So what happens with this command over here is I'm selecting only those records where this condition is met. And if this condition fails, I will omit those records. So I hit enter, and if you look at this particular column, you shall see that all of the values are greater than 5. So this was a simple information drawing that we did. Now, similarly, if I want to see only all of the species which are of type Setosa, I can also do that. So here I'll have iris, species, and species. Since I want only Setosa type species, I'll set this to be Setosa. And I would want to extract all of the records where the value is true. Let's see what do we get. So here, if you have a glance at this, you will see that all of the species are Setosa, right? And the indexing, it ranges. So this is the starting index, which is 0. And then the ending index is 49. So the index, it ranges from 0 to 49. And there are, out of the 150 records, there are 50 records for the species Setosa. So this is interesting. Now, I'll have a glance at the original data frame again. Let's see what other inferences that we can draw from this. Okay. Now, let's say if I do want to understand or have a look at those records where the petal width is greater than 1 and the sepal width is greater than 4. Let's see if any such record exists. I'll have iris, and here the first condition would be sepal width should be greater than 4, and I shall given the next condition, which would be petal width should be greater than 1. Let me put these in braces. Let me hit enter. Let me give in and over here. Okay, seems like most of the values are false. Let's see if even a single record exists where the sepal width is greater than 4 and the petal width is greater than 1. Seems like we have 0 such records. Okay, 1 seems to be too high. Let me keep it to be 0.5. Does not work again. Okay, let me keep it to be 0.3. Okay, seems like we have one record where sepal width is greater than 4 and petal width is greater than 0.4. Interesting, right? So this is only one species of Setosa where your sepal width is greater than 4 and petal width is greater than 0.3. This is a really interesting observation that we've made. Similarly, if I were to maybe reduce this a bit, instead of 4, I'll keep it to be 3.5, and this I'll set to be 0.5. Okay, this is an interesting observation. So here we see that these are all species which belong to Virginica, and here the petal width is greater than 2 or equal to or greater than 2. Right, so the petal width for this is 2, 2.2, 2.5, and the sepal width for these are 3.6, 3.8, and 3.8. Interesting observation over here. So all of this we were able to do with the help of pandas. And now we shall also go ahead and do some visualization. So I will again have a glance at the data frame iris.head. I'll start off by having a glance at all of the individual columns. So for this, I would want to make a histogram. So I have the histplot method inside this, since a histogram will require only a single column and that has to be a numerical column. So I'll start off with the sepal length and I'll map the sepal length column onto the x-axis. I shall given the name of the column, which is sepal length. And then this is coming from the iris dataset. I would just have to show this out, plt.show. Let's have a glance at this. This will take a bit of time. Okay, so this is what we get. So here, this is sort of a bell curve, not exactly a bell curve, but almost close to a bell curve. We see that most of the values, they are closer to 6, and there are very few values of sepal length which are greater than 7 or less than 5. Right, so this is a really interesting observation that we can make from here. Now, if I do want to change this and maybe have a glance at all of the three different species. So what I can do is I can set the hue to be equal to species. So here this is how we get it, right? So here seems like the highest sepal length or this, so 6 to 6.5, this seems to be for versicolor, and here for Virginica, the sepal length seems to be from 6.5 to 8. Similarly, for the species Setosa, the sepal length seems to be around 4.5 to 5. And most of your values here, so there is an intersection of these three, right? So the intersection for Setosa, versicolor, and Virginica is here, and that is why. So there would be around 15 or 16 species of flowers whose sepal length is closer to 6. So this is a really interesting observation that we've made from this. Now this was the sepal length column. Similarly, I'd want to look at the sepal width column. So again, I have SNS dot has plot, and onto the x-axis, I shall map. So the next was sepal width, SEPAL. Let me give this in. I would also have to give in the name of the data set, else this will not know where the column is from. Data would be equal to iris, and I shall type in plt.show. Again, a very interesting observation over here. So we see that most of the values, they are centered around 3 to 3.2. So we have around 35 values whose sepal width would be around 3. And then there are very few values whose sepal length is greater than 4. And similarly, there are very few values whose sepal length is less than 2.5. Again, we'll have a similar observation for petal length and petal width. So let me copy this from over here. Let me change this to be petal length. And then let's have a glance at the result. Okay, so this is a very interesting observation over here. So here we seem that, so the petal length, so there seems to be a break over here. This is not really continuous. And then you have one peak over here. So most of the petal length values, they seem to be between 1 to 1.5, and there are more than 40 such records. Similarly, you have petal length values ranging from 4 to 5, and there are 30 such values. Interesting observation. Okay, so this was petal length. I would also need to look at petal width. I'll type in petal width. Again, there seems to be a break over here between 0.5 and 1. And most of the values, their petal width seems to be between 0.1 and 0.4. And you have 40 search values. And then you have another peak over here, which is between 1.2 to 1.5, and you have 25 such values. So this is what we were able to understand by having a glance at the individual columns. Now, similarly, what we can do is we can understand the relationship between two such numerical columns. So for this, we can go ahead and make a scatter plot. So here, I will type sns.scatterplot, and I would have to map something onto the x-axis. So I will map sepal length onto the x-axis, and then I would also have to map the petal length onto the y-axis, and the data is coming from the iris data set. I'll have plt.show to show this image, and this is what we get. So it seems like there is a linear relationship between petal length and sepal length. So as the sepal length of this species increases, or this flower increases, the petal length also increases. Now, to get more information from this data set, what I can do is I can change the color with respect to the species column. So I'll set hue to be equal to species, and we see that this blue color indicates all of the Setosa species, orange indicates all of the versicolor species, and green indicates all of the Virginica species. And it seems that all of your Virginica flowers, they seem to have the maximum sepal length and the maximum petal length. And then your Setosa species, they seem to have the minimum sepal length and minimum petal length. So this is an interesting observation that we've made from this data set. Now, going ahead, we've looked at sepal length and petal length. I can also change this and make it between sepal width and petal width. Let's see if there is a similar relationship between these. Okay, interesting observation over here. So here seems that the least petal width is for Setosa, and then you have versicolor in between, and then at the top you have Virginica. And now, also, but another interesting point over here is the highest sepal width also seems to be for Setosa species over here. So least petal width is for Setosa, and also the highest sepal width is also for Setosa. So that is an interesting observation that we've made. So this over here, this would become an outlier because most of your values are greater than 3 or somewhere around the 3 mark. So they range from 3 to 4. So this will become an outlier because this is below 2.5. So we've looked at this, and then what we can do is we can probably make a box plot as well. So we can have a categorical column onto the x-axis and a numerical column on the y-axis. SNS dot box plot. I will have something on the x-axis. So species is the only categorical column that I have, and I shall map that onto the x-axis. And on the y-axis, I want to see how the sepal length varies with respect to the species column. And obviously, these two columns are coming from the iris dataset. Here, I'll again type in sns.show and let's see. Right, so this is an interesting relationship that we get. So here we see that this is what we actually understood through the above graph as well. So Virginica has the highest sepal length. So this over here is an outlier because most of your values, they range between 6 and 7.5. This is only one such value, which is below 5. And again, Setosa has the lowest sepal length. So this ranges somewhere between 4.5 and 5.5 over here. Again, if I were to change the colors, so I'll use the hue attribute over here. And inside this, I shall pass in the species column. So I'll have a different color for each box. Now, if I wanted a same color for all of the boxes, and if I wanted to change it, I'll use the color parameter over here. Let me change it to pink, and let's see how does it actually look. Well, this is how it looks. Interesting. Okay. So we've also done some data visualization. Now it's time to go ahead and build some models on top of this. So we shall be building a regression model and also a classification model, and we'll understand the results. So for this, I would need another library called as sklearn. So let's go ahead and use that. So from sklearn dot model selection, so before we actually go ahead and build the model, we'd have to divide the data set into training and testing set. And that is where this submodule model selection will give me a method called as train test split. So from sklearn.model selection, I am importing this. And what I'd have to do is I would have to extract the X and Y variable from the data set. So iris, let's say I would want to extract what would I need? I would need the sepal length column, and I shall also need, let's actually just take the sepal length column, and I'd want to understand how does sepal length vary with respect to petal length. So sepal length, I'll actually put this in the x-axis, and in y, I'll have petal length. So I shall take the petal length column. Let me pass this in two braces. I need a 2D matrix or a 2D array. Okay, so I've extracted the sepal length column, stored it in the X variable, extracted the petal length column and stored it in the Y variable. I can go ahead and pass these into the train test split method. Let me use this. First parameter is X, second parameter is Y, and then the test size would be 0.3. And this will give me four values or four returns. And then the first one would be X train. Then I shall have Y train, and this will actually be X train and X test. Then I shall have Y train, and then finally I shall have Y test. So X train is the training set for your X variable or independent variable. And over here, X test is the test set for your independent variable. Y train is the training test for your dependent variable. And Y test is your testing set for the dependent variable. Okay, we've got this. Now we can go ahead and finally fit the linear model on top of this. Okay, so for this, I'd have to import the linear model from sklearn dot linear model. The name of the ML algorithm is linear regression. I'll go ahead and import this and I shall create an instance of this. I'll set LR is equal to linear regression. I'm creating an instance of it and I'd have to fit this model on top of the training set. So LR dot fit, the training set comprises of X train and Y train. I've fit the model. Okay, seems like we've successfully built it on top of the training set. Now it's time to predict the values on top of the test set. So I'll say lr dot predict, and I shall be predicting on X test, which is basically your test set for your independent values. And this will give me the predicted values, which I shall store it in a variable called as ypred. So to compare these two values, I'll show you the actual values and the predicted values. Actual values are present in ytest. I'll have a glance at the first five values, and then the predicted values are present in ypred. So I'll select the first five records from that as well. And let's see what is the difference between the actual values and the predicted values. So here the actual value was 4, predicted was 3.09, actual was 5.1, predicted was 5.7, actual 3.7, predicted 3.09, actual 5, predicted 4.6, actual 5.1, predicted 4.05. So you see that there is definitely an error in prediction, and this is known as residual. Now, when it comes to linear regression, we go ahead and square all of these residuals and sum them up, and that is known as your residual sum square. Now, when you take mean of it, what you get is mean squared error. Now, the model which has the lowest mean squared error or residual sum error, that would be your best fit model. So, for this, we can just go ahead and use the mean squared error method from sklearn dot metrics import. I have something called as the mean squared error. I'll use this method, and inside this I shall go ahead and pass in the values. So I shall have the actual values which are present in y test and the predicted values which are present in y pred, and this is the mean squared error that we get. Now, what you can do is you can do trial and error and change some hyperparameter values over here, and you can create a different model and compare the mean squared error of that model with this that you've just built. Okay, so this was linear regression. Now let's go ahead and also build a decision tree to classify this data set into either Setosa, versicolor, or Virginica. So this time I shall be changing the x and y values. So for this x actually let's keep it to be sepal length. So that will be same. Now in y, I would need the species column. So I am getting the species column from the iris dataset. Let me just show you the X and Y values over here. So X is sepal length and Y is your species column. That is what we have. Now going ahead, again, I would have to create a train test split for this. Train test split X and Y. And then the test size, let me set it to be 0.35. So 30%, 35% of the records will go into the test set, and 65% of the records will go into the training set. Now, this again will give me four values: X train, X test, Y train, and I shall have Y test. So these are the four returns which this method gives me. Now I would have to again fit the model on top of the training set. And since this is a decision tree, I'd have to import it from sklearn dot tree. I am importing something called as the decision tree classifier. So decision tree classifier helps us to create obviously a classification model on top of this. And again, let me go ahead and create an instance of this. I shall call this as DTC. I shall use this method, decision tree classifier, and I can go ahead and fit this model on top of the training set. So I'll have DTC dot fit X train, and I have Y train, and I've been able to fit this model on top of the training set, and then we'll go ahead and predict the values. So I'll have DTC dot predict, and I'm predicting this on top of X test. And you see, this is the result. So I'm predicting each record to be either versicolor, virginica, or setosa. I'll store this in a new variable, call that to be Y pred. Okay. Now, this time, instead of mean squared error, I will use something called as a confusion matrix and accuracy score. So I'll show you what that confusion matrix actually is from sklearn dot metrics. What do I need? I would need a confusion matrix. And inside confusion matrix, I shall pass in two values. One is the actual values which are present in Y test, and then I shall have the predicted values which are present in Y pred. And this is what we have. So here, this value 12 means that actually the species is setosa and it was predicted to be setosa. Then you have versicolor. So actually the species is setosa, but it was predicted to be versicolor. This is for virginica. So actually it was setosa, but it was predicted to be setosa. So this is predicted to be virginica. So you see that no such records have been misclassified. So these two indicate values which have been misclassified. So setosa either misclassified as versicolor or virginica. And over here, this will be for versicolor. So this over here 9 indicates all of the records which were actually versicolor and predicted as versicolor. So this is for those records where actual was versicolor but was predicted to be setosa. This is for those records where the actual was versicolor and it was predicted to be virginica. And here the final one, this you see, this is all of those values where the actual record is virginica and this was predicted to be virginica as well. So basically, this left diagonal is all of those records which have been classified correctly, and the rest of the values are those which have been misclassified. So if you want to understand or calculate the accuracy, basically sum these up: 12 plus 9 plus 9, so that would be 18 plus 12, so that would be 30. 30 divided by all of the values, and you shall get the accuracy. Now, we don't have to do it manually. We have a method called as accuracy score. I shall go ahead and also import that from sklearn.metrics import. I would have something called as an accuracy score. And inside the accuracy score, I shall pass in two values, which would be the Y test, which are the actual values, and I would have to predict something. So, which is Y pred. You see that the accuracy is quite low. So it's only 56%. Now, what we can do is we can go ahead and change our x and y values. So, we were here basically trying to classify this as Setosa versicolor and virginica on the basis of only the sepal length column. Now, I'll change this. So, here, let's see where was the x. So, here, x was iris of sepal length. Now, instead of this just being a sepal length, what I'd want to do is I'll add more variance into this or more influence towards the x variable. So instead of this just being a sepal length column, x will be equal to sepal length, and also let me add petal length. Let me do the entire thing again. I'll run all of these. So initially, what we got, the accuracy was 56%, and let's see if there is any change in this. Wow, you see, suddenly the accuracy has increased. Initially, we had just used the sepal length column. This time, we have used the sepal length as well as the petal length column, and the accuracy has increased. So, accuracy has become 86%. Let's include more columns now. We have sepal length, petal length, and I shall also include the sepal width column. I shall have sepal width, and let's see what would be the accuracy now. Well, the accuracy has increased again. So from 86%, it has increased to 94%. So this is the trial and error that you can do or change your hyperparameters and then play with your models. So friends, in this particular session, we've done a bit of data manipulation, we've done data visualization, and then also built linear regression model and the decision tree classifier. So this was sort of an end-to-end project where we've gone through the entire data science lifecycle. So thank you very much. And if you've liked this session and you thought that this was helpful, do hit the like button. And also do not forget to share it with your friends and family members and also subscribe to our channel. Thank you very much. And